Yeah, sir is there. Yeah, you can start, Japmala.
Okay. Good evening, everyone. Department of Mathematics, St. Anne's College for Women, takes this privilege in welcoming you all to the third day of National Level Lecture Series, Igniting Young Minds Towards Mathematical Research. In our midst, we have Dr. Satya Prakash Singh, Assistant Professor, Department of Mathematics and Statistics, IIT Kanpur, to share his expertise in motivating and inspiring students. Let us begin the session by invoking the blessings of Lord Almighty. May I invite Mrs. Saujanya, Assistant Professor, to lead us into prayer.
Thank you, Japmala. Today's scripture portion is taken from 1 Thessalonians chapter 5, verses 8 to 11. We belong to the day, and we must be sober. We must wear faith and love as a ring, and our hope of salvation as a helmet. God did not choose us to suffer, but to possess salvation through our Lord, who has risen for us in order that we might live together with him, and so encourage one another and help one another, just as you're now doing. This is the word of the Lord. Thanks be to God.
Thank you, Saujanya. May I have the pleasure of inviting you, sir, with virtual floral greetings. It is with deep pride and humility that I introduce eminent speaker for today's session, Dr. Satya Prakash Singh, Assistant Professor, Department of Mathematics and Statistics, IIT Kanpur. Dr. Satya Prakash Singh received his doctorate degree from the Department of Mathematics, Indian Institute of Technology, Bombay in the year 2016. He then worked as an assistant professor in the Department of Mathematics, IIT Hyderabad. To continue his research, Sir served as a postdoctoral researcher at the Department of Statistics, University of Haifa, Israel. Currently, Sir is working as an assistant professor in the Department of Mathematics and Statistics, Indian Institute of Technology, Kanpur. Sir has published 16 scientific research articles, including books and journal papers. His research work is associated in the field of optimal design of experiments related to crossover trials, cluster randomized trials, longitudinal studies, and the audit experiments. His teaching interests includes regression analysis, time series analysis, statistical analysis using R, linear and nonlinear models. I once again welcome you, sir, to address the participants. Over to you, sir.
Yeah. Okay, thank you, Japmala, for this nice introduction.
Thank you.
First, I would like to thank to the organizers for organizing this wonderful seminar. And I think the kind of lectures we are having in this seminar, they are very useful, especially to the students. And also, it's a very good way of interacting with the young minds and motivate them to do some further research, or if they are interested, they can go to their respective fields. So let me start my talk. Just hold on, let me share the screen. Okay, okay. I think just confirm if you can see.
It is visible, sir.
Okay. So in today's talk, I will talk about basically the regression methods. That is a very essential component of data science. And in this talk, I will not talk rigorous mathematical concepts, but I will give you an overview where these regression methods can be applied, what kind of practical applications we have where these techniques can be useful. Okay, and if time permits, we can cover a part where we have a bit detailed about some mathematical detail about regression. Okay, so I will start. So in this talk, more or less, I will talk about only the data analysis, basically the real life examples where we have we can apply these methods, regression methods. So for this purpose, just to motivate these methods, I included several examples. So let me start with the first example. Okay, so in this example, we have a person, just call it as an industrial engineer, and the job of this person is to figure it out that there are vending machines, and to fill a vending machine we need certain times, and the job of this person is to identify that how much time a person is needed when he is going to fill the product in a vending machine. Okay, so here the particular person is interested to know how much time is needed to fill a vending machine. Okay, the product that are filled in the vending machine. So this is a kind of experiment we have. Okay, so this will help you. Suppose if you are able to predict this scenario, that if a vending machine required this much product to be filled, then we are able, then this is the on average this much time is needed. Okay, if we know this information in advance, so we can use this for better service. Okay, so in this case, what happened? This person collected the data from 25 different vending machines. Okay, so he or she went to the vending machine, and there was a registered where if a delivery person is coming to fill the product, he just mentioning the time at which he started the process, and after filling he just noted the time that his job is done. Okay, so we have the data set where this much time is needed and these many products are filled in the vending machine. Okay, so in this case, the job of this engineer is to figure it out how much time is needed to fill a this vending machine for a given number of products. Okay, so just hold on. Okay, yes. So this is the data set. So in this data set, the first column represents the number of observations. So for example, in the first case, in the first vending machine, there were 7 cases, 7 products that were filled, and it took around, here the time is in minutes, and it took around 16.68 minutes. Okay, and similarly, we have all these 25 data points. If number of cases is 3, then this much time is needed, 11.5. Okay, so of course, here one can of course logically predict that if the number of cases are more to be filled, then it requires more time to fill all the cases. Okay, but how much? Okay, if we have a very precise kind of answer to this question, then this information is very useful. Okay, so how we do that? Okay, so to answer this type of questions, we need the regression techniques. Okay, so here in this case, I just mentioned that this example falls under the category. If you read the first line, the heading of the title of the slide, in the bracket it is simple linear regression. So why this is simple linear regression? Because here we have only one variable that need to be predicted, which is time, and we suspect that it depends only on one variable, that is the number of cases to be filled. Okay, so if we have this scenario where we have only one response, we call the dependent variable that we are trying to predict as a response variable or a dependent variable, and we are trying to model this with the help of some independent variables. So in this case, the independent variable is the number of cases to be filled. Okay, so suppose if you have only one response and only one regressor, one independent variable, one dependent variable, and one independent variable, then it falls under the category of simple linear regression. Okay, so suppose, so in this case, this person thought that this is the only thing that is affecting the time, but there are several other things that might be affecting the time. For example, the distance from the warehouse from where the person is collecting all the products and going to the vending machine. So the distance from the warehouse up to the vending machine, that is also a very potentially very kind of significant independent variable that might be affecting the time. Okay, so and not only this, we have several other factors. For example, the route he's taking, the kind of vehicle he is using, and the route, if you have a lot of traffic or not. So there are many more factors that are actually affecting your response variable. Okay, so if you add more than one regressor in your model, more than one independent variable in your model, then that will become multiple linear regression. Okay, so for example, in this same example, if we add the distance also, and I have that example also, then that will become multiple linear regression. Okay, so this is the kind of scenario where we can apply regression techniques to to answer this question. What is the question? That how much time is needed, basically, given this much number of cases. Okay, so here I just plotted the scatter plot where of this time versus number of cases. So here it is, of course, it is almost intuitive that as the number of cases increases, you will have more time to fill the vending machine. And this is what we are having here. If we have, say, for example, 30 number of cases, then of course you need more time, around more than 70 minutes. Okay, so and not only this increasing trend is there, but what else you can see from here? You can see that the relationship is almost a linear relationship. Okay, so if one of the things, if you have a data and if you are able to plot it, so the first thing you start by plotting. So plotting will help you actually to get some idea about the behavior of this data. Okay, so from here you can easily see that the linear relationship might be a very valid relationship. So we will try to fit a straight line that passes through these points as close as possible. And this is what basically what we do in the regression analysis, especially in simple linear regression analysis. That is called least square estimation. We'll talk about it. Okay, so I hope that this is clear. This what is going on in this example and what is the question and how to answer. I think this is clear. Okay, so now again, this I already explained, but let me spend some time on this. That suppose this person also suspected that the time is also maybe a function of the route or the distance from the warehouse and to the vending machine. Okay, so now in this case, he also measures the distance, and you can include this as another factor in your regression model. Okay, so you have the data that is for the distance. One, you already have these two. One is dependent variable, cases is there, and another independent variable you added, that is distance. Okay, now if this is the case, then as I said, this will become a multiple linear regression. Okay, so now you might be thinking that, of course, if we are adding a very reasonable variable that might be affecting your time, of course this will increase the predictive capability. Your prediction will be good. Okay, so in the process of regression analysis, any regression analysis, First of all, you start with a bunch of independent variables that you can thought of might be affecting your response. Response means the variable you are trying to predict. Okay, some of them might be relevant, some of them may not be irrelevant. Okay, so in the process of regression method, regression analysis, we also get to know that out of given certain number of independent variables, what is the set of variables that is actually relevant, and there is a set of variables that is not relevant. Okay, so it is not only fitting the model, but it is more than that. It will also tell you the significance and insignificance of the other variables, which should be included in your model and it should not be included in your model. Okay, but distance seems to be a very reasonable variable, so let's include this also. There might be another factors that you can think of, and we already discussed. Just try to include as many as possible, and later you just in the process of fitting the data, you will see that those who are not affecting the time will get removed automatically. Okay, so in this case, because now you have one dependent variable and two independent variables, then if you plot this scatter plot of this data, this will look like this. Okay, and this is not that useful because from here you cannot see exactly that what is the relationship between y and between the dependent variable and the independent variables. So there is something called contour plots. So from those plots, actually, in case of more than one variable, you can also somehow, to some extent, get an idea that is there any linear relationship there or not. Okay, but I'm not going to detail in the contour plots. So let's move on. So I hope that this is clear. That this is, and if this is the case, then here we fit a multiple linear regression model. Okay. So far, what we have assumed here, the response, if you look at this response, the delivery time, the second column, this looks like a continuous variable that can take value, any value from 0 up to any value it can take. So here, the response, we say that is continuous in nature. Okay. If the response is continuous in nature, we usually try to fit it using simple linear regression. And later we assume some certain condition on the response also for the to test the significance of the variables. And we assume that they are coming from some normal distribution. Okay, so this is one of the scenario where your response is continuous in nature. Okay, let us talk about a different scenario. Okay, so just let me go through this example. This is another example where your response is not a continuous type, but in fact it is binary in nature. Okay, so this example I took from a paper. It is that published in 1959, and it is also used in one of the book that is very good book that covers all these topics. A book by, I have that reference also, book by Montgomery. So from there I took this example. So in this example, what is happening? Okay, so there is a disease called pneumoconiosis. Okay, so this is a lung disease, and a person will have this disease if the person is more and more exposed to the dust. Okay, so in this experiment, the authors want to know that certain if there are certain miners, they are working in a coal mine, and they want to know that what is the relationship between the number of years, number of months they are exposed to the coal mine, and they have this disease. Okay, so in this case, the question is, what they have the data about of some miners. Okay, so for those miners, what they have done, they have collected the data something like this, that how many years they were exposed to the coal mine and whether they have this disease or not. Okay, so in this case, your response is of binary type, where if the person is having this disease, we call it 1. If the person is not having this disease, we call it 0. Okay, so in this case, a response is binary in nature. Okay, so to fit the model, we need something else, something different than linear regression, simple linear regression, and this falls under the category of logistic regression. That's why in the bracket I have written logistic regression. So this example is basically falls in this category, logistic regression. So let me talk about the data set. So here the first column will tell you the number of months that a person is exposed to the mine. Okay, so here, and whether they are having this disease or not. Okay, so just read this first row here. 5.8 means these many months. Okay, 5 years 8 months a person is. So there were 98 miners. Okay, they were exposed to the coal mine for this much time, but they don't have that disease. Okay, so here the second column tell you that out of 98, how many of them actually are having this disease. Okay, so in this case, out of 98, no one shows the symptoms that they are diseased. Okay, so in this case, the number of proportions, and we can talk about the proportion also, that out of 98, how many of them are actually affected by this disease. So in this case, if 5 years 8 months, nobody is affected. Okay, now let's move on. Now if they are exposed for, I think this data is for months, for 15 months, there were 54 miners. They were exposed to the dust for 15 months, and out of 54, only one was declared as that person is having this disease. Okay, and similarly, you can see, you can read all these columns. So here we have this respective proportions. So you can think of these respective probabilities. That the person is, what is the probability that the person will expose to this disease, given that he is spending this much time in the mine. Okay, so as from here you can see that if they are spending more time in the mine, they are likely to have that disease. Okay, so again here if you plot the data, plotting data means here in the x-axis we have the years of exposure, and here I think this is month, it should be month, and here in the y-axis we have the proportion that they will have this disease. Okay, so in this case also, now suppose you are interested that somebody is telling you that okay, come for this job and for this coal mining job, and you have to spend this much time. Okay, then from this data you can get an idea that whether you will more likely to have this disease or not. According to this, you can choose this job. Okay, so so this kind of answer you can get from this regression method. Okay, so I hope that this example is also clear. Okay, so now next we have in this case we have seen that two types of responses. One is continuous, that can take any value, and then another is where the response is taking only two values. Okay, there are certain other scenarios. For example, your response or the dependent variable can take values in a form of count data. Okay, so for example, number of accidents that are happening on some certain road. So if your response is in between continuous and binary, if it is of the type of count, then then also you can use this technique. Okay. And basically, then that more or less that technique falls under the category of Poisson regression. So Poisson distribution deals with this count situation. Okay. So here we have another example. So this example, it is also from the same book that I just mentioned, this Introduction to Multiple Linear Regression Analysis by Montgomery. So they mentioned this example, and in this example, they quote this example. So what is happening in this example, that during this Vietnam War, US Navy operated two types of aircraft. Aircraft means they were supposed to attack certain locations. So they have used two types of aircraft. One is called the McDonnell Douglas and A4, and second one is the Skyhawk and the Grumman, which is A6. Okay, so let me just now onwards, I will just refer two types of aircraft. One is A4 and another is A6. Okay, so in this case, in this example, we have the regressors. Regressors X1 is, we have three regressors, three independent variables. I will talk about what is the objective, what is the response. First, let me talk about what are the independent variables. Okay, the independent variables were that which type of aircraft was used. We have two types, A4 and an A6. So X1 is the indicator variable that is basically telling you that A4 is used or A6 is used. If A4 is used, then it will take value 0, and if A6 is used, it will take value 1. Okay, similarly, we have X2 and X3. So X3 is the variable that is basically telling you that what is the capacity of that aircraft to take the load, bomb load. Okay, so X2 is the bomb load in tons, and X3 is the variable which is the total months of air crew experience. Okay, so each aircraft is consists of air crew and how much experience they are. Okay, so these are three regressors, three independent variables, and the response is the number of locations where damage was inflicted on the aircraft. Okay, the number of locations where the damage was happened. Okay, so in this case, you can see that it is not continuous because this damage is a kind of count data, and it is not binary in nature. Damage can be 0, can be 1 at one location, that can be 2 locations, can be 3 locations, 4 or 5, something like that, something like this. So in this case, your response is not binary in nature, not continuous in nature, but it is of the count type of data. In this scenario, we will use something called the Poisson regression. Okay, so but all these categories falls under the category of regression analysis. They all we can also fit the model in all these situations. Okay, so I hope that these 3 examples are clear. Okay, now let me, okay, so this is the data set they had. And let me talk about another example. And where in all of these 3 cases previously we talked about, there we are able to fit a linear regression model. Okay, but there are certain situations where this linear relationship may not hold, and for that we have to fit a model using something called nonlinear regression. So here we have one example. Okay, just to indicate that there are situations where you may fail to fit a regression model. Okay, so in this case, the response is this is the these are the authors, and they were doing some kind of a kinetic chemical kinetic experiment where the response was the velocity and the regressor dependent variable was the velocity, and the independent variable was the concentration of the substance. Okay, and here the aim was to fit a model that predicts the velocity for given concentration. Okay, now from here This is the data set. The first column is consists of the concentration, and velocity. You can see that there are two columns. So just concentrate on any of them, because this is the multiple measurement we have taken at the same concentration. So for example, when concentration is 0.02, we have measured the velocity twice. Okay, so those velocities are reported. Okay, but let me plot this data. Okay, so this is how the data will look like, concentration versus velocity. So here you can see that a linear fit may not be a very good fit, because we have a curved shape of data. The relation between y and x is it's bit curvy. So in this scenario, even if you try to take some kind of transformations and you just try to figure it out if linear regression can be fitted, but you will see that it cannot be fitted, and we have to go for the nonlinear regression. Okay, so more or less, we have these 4 type of situations. Of course, there are many more situations, but if these are the situations we have, we can use the regression technique to fit the model and to have some kind of very good prediction about your response. Okay. Now, okay, so the summary of these examples is that for the first example is a linear regression model can be used. In the first example, a linear regression model can be used. And for the second and third, logistic and Poisson regression models can be used. And both of these two models, including the first one, are come under the category of generalized linear model. If you do any course related to these topics, you will see that there is a term called generalized linear model. So they all fall under this category, generalized linear model. Okay, and the fourth model is basically it is different than these first three, and this falls under the category of nonlinear regression, where you cannot fit a linear model. Okay, so I hope that we have enough examples to motivate you why we should use regression methods. Okay, this is because this is a very powerful technique to predict the responses. Okay, now let me. Okay, so this is, I have talked about this also. Let me, if we have time, let me discuss some mathematics behind one of the situation, and let us consider on the simple linear regression case. Okay, so basically what we do in simple linear regression, we are trying to fit a straight line, okay, that has a very good prediction. Okay, so let me discuss the process. So this process involves something called the least square estimation. Okay, what we do in least square estimation? First of all, we should have a data set. Okay, all these techniques, all this model building is basically all of them are data driven. Okay, so here we have a data set of the type xi versus yi. Okay, so yi is basically the response and xi is basically your independent variable. Now you can think of y as a time and x as a number of cases. And this n is equal to 25 if you correlate to the first example. Okay, so we have this data point, and your job is, first of all, your job is to predict y based on this x. Okay, so what is this x? Okay, what we do? Okay, so suppose you have more than 2 regressors, more than 2 independent variables. Okay, then we have to think of a function that is f, okay, which is a function of these independent variables, and there must be some unknown parameters that I am denoting by beta. Okay, so this we have to first come up with a function, okay, that you think of may be very good for predicting. Okay, now if we are in the setup of linear regression, so we have to use a linear function. Okay, so but here I am talking about a general setup. Now here this f can be nonlinear also. Okay, but your job is to first of all, to find a function f such that your y is fitted by this function f with the help of x and those unknown parameters. Okay, this is what we do in the linear least square estimation. Okay, so now, as I said, that the time taken by a person to fill the cases. Okay, even if you include all the relevant regressors in the model, there might be something that is unexplained. Okay, so can you imagine that if you include whatever the causes you can think of that are affecting your time, will able to explain the time? You included the distance, you included number of cases, you can include the person, gender also, you can include the route also, weather condition also. Then also there must be something that is unexplained. Okay, so if you are able to include all the variables, then you are able to fit the model, a perfect model. Okay, but this is impossible, next to impossible. So there are always a chance that there must be some error. Okay, error between the response and the model you are trying to fit, the relationship between these y and these xi's. So we call this as EI, the difference between the function you have and the response you have. Let me call this EI. Okay, so what we do in this least square estimation, we are trying to minimize the square of sum of the square of these error terms. That's why it is known as the least square estimation. Okay, so here what is given, what we have in our hand, we have yi's, we have xi's. What we don't know, first of all, we don't know the form of f, and we don't know what is this beta. This is unknown. Okay. Now, since we are talking about linear estimation, we assume that the relationship of this f, the f that is representing the relation between x and beta, is linear. Okay, so, and if you are talking about simple linear regression model, then this f will of this form, where we have beta naught plus beta 1 x. X is your independent variable. Okay, so here we assume, so we have to start with a function that is known to us. Okay, so if it is simple linear, we have this form. If it is multiple linear regression, we have to add another variable, something called beta 2x2, then beta 3x3, and so on. But this is, we have to add, okay, because we are doing linear regression, simple linear regression. Okay, now here in this model, beta naught and beta 1 are unknown. Okay, and if you just replace this value of f in this expression in s beta, you will get this last expression. Okay, just a bit of just try to just fit this EI, the first EI that I defined in the first equation, in this expression, and the form of f, you will get this last equation. Okay, so here I am denoting this as s beta because beta, this bold beta is a kind of vector that has component beta naught and beta 1. Okay, so here we see that this is a function of beta only because you know y's and you know x. Okay, now your aim is to minimize this function with respect to beta naught and beta 1. Why? Because your job is to minimize this error. If this error is very small, this implies that this function is very much capable of explaining of the dependent variable y, isn't it? Okay, so how we do that? If we have this type of function and somebody is asking you to minimize this, what will you do? Okay, so before talking about the minimization of this, let me give you another interpretation. So what we do in the least square. Okay, so suppose here, just think of these as the time delivery data set. So these blue dots basically, so here we have these scatter plots. of the data set, and you are interested to fit a line that basically passes from this data point, this data set, such that the distance between from this line to these data points, you square it and sum it, is minimized. Okay. Okay, so again, there are several kind of other scenarios that why we are interested only squaring of the distance, because there are other methods of measuring the distance also. You can take the absolute difference, not the square. But there are some certain maybe difficulties if you have some other kind of distance measures. For example, if you have mod absolute difference, then that function is not differentiable. You cannot differentiate it. You cannot easily do the optimization. But if you are taking this square, that is you can do this differentiation, and also square is a convex function, and sum of the convex function is again a convex function. So the whatever the optimal solution you will get, that turn out to be global optimal solution. So there are good things about this type of function that is called the least square estimation. Okay. Now, so what we do if we have a function that we are trying to minimize, we should use this technique, derivative technique. So we just differentiate the objective function, which is our S beta in our case, with respect to the parameters of interest. So if you do that, if you just try to differentiate it with respect to beta naught, you will get equation number 1. And if you differentiate it with respect to beta 1, you will get equation number 2. Okay. Now you have 2 equations and you have 2 variables. Now you can solve it. And if yi's and xi's are well behaved, then you will get a unique solution also. If you just try to find a matrix that turn out to be invertible, and you are in a safe situation. So after a little bit algebra, if you solve this, you will get the solutions. Okay, so these equation number 1 and 2, they are called the normal equations. And if you solve these 2 equations, you will get the values of beta naught and beta 1 that are given in equation number 3. Okay, so beta 1 is beta. Now I'm denoting this as hat because now they are dependent on the data. Okay, so hat basically this notation is used for the estimated values. Now you can think of this is the solution of equation number 1 and 2, and these are known as the least square estimates, least square estimators of beta naught and beta 1. So beta 1 hat has this sxy upon sxx, and I have explained in below that what is these expressions. Okay, so this expression looks a bit messy, but this is the standard. These are the standard least square estimators. Now from here, given the data set, you see from here you can see to get these estimators, what are the things needed? You just need yi's and xi's. That's it. Okay. So from the given data set, from yi's and xi's, you will get the values of beta 1 and beta 1. Okay. And these are known as the least square estimators. Now you have those estimators in your hand. Okay. Now again, so from here, this is okay. Normal equation, you solve it, you get this least square estimate values. Okay. So now you have to do some kind of verification that this solution is actually minimizing your error, minimizing your S beta. So for this, we have something called the second derivative test. So we have to take the second derivative and we have to check this condition number 4. Okay, so from here, okay, so the one square is missing. I'm sorry for this. So in the equation number 4, we have summation of 4 and summation of xi minus x bar to the whole square. Okay, and if this is greater than 0, then and if along with this, if we have this equation number 5 also, then we say that this solution will satisfy this solution minimizes your objective function. So we have these conditions also. Whenever we try to optimize this, we have to find the solution based on the normal equations, and then we have to put this solution to the second derivative of that function to test that whether this solution is actually minimizing your objective function or maximizing. So in this case, if they both are positive, then this solution will minimize, and not only minimize because your function is convex. Then from this method you will get a local solution. Okay, this derivative method always tell you the local solution, but your function is convex, then this local solution will become a global solution. Okay, so these are your estimators that will globally minimize your error. Okay, now coming back to this delivery time data, if you apply this method to that data, you will get beta naught. The estimate of beta naught and beta 1 as this. Beta naught is 3.32 and beta 1 is 2.13. Okay, now your fitted model is given here. This is the question. Y hat will be equal to 3.32 plus 2.17x. Okay, so from here, okay, now suppose if you put x equal to 0. This means if there are no cases to be filled in the machine, then also the person needs 3.32 minutes. Okay, so this is what the intercept is, and this is the 3.32 is the intercept, and 2.17 is the slope of this line. Okay, now if you increase x by x plus 1, so this implies that if you have another case to be filled, given that suppose 7 you have to fill 7, but there is another extra case, then how much time more needed to fill that particular extra case is 2.17. Okay, so from here, this is the fitted model based on the data. You have fitted the model. Now from here, from this model, you can actually predict that. Just put the value of x is number of cases, you will get the estimated value of time, needed time. Okay, so I hope that this is clear. So from this is a very simple example, but this will explain the need of such methods. Okay, so here based on this data, if you fit the straight line, this is the blue line, you can see that is the fitted line, and you can see that it passes through very closely, passes through all the data points. So this turned out to be a good fit, but there are some other measures also that will tell you that this fit is basically a very good fit or not. That is called something called R square. That if R square is very high, then we say that this fit is a very good fit. Okay, so this is all about today's talk, and this is the book. Somebody is interested, that then can go and read this book. And this book basically covers all the technical details, mathematical details of all the scenarios, whatever I have covered in this talk. And this is a very nicely written book. And that's it. Thank you for your attention. So this is all for today. And if you have any questions, just please let me know.
Thank you, sir.
Yes.
Any questions from participants?
Sir, can I ask you a question?
Sure, sure.
Sir, actually in semester 6, we have for our students from next academic year, we have project work, sir. So
Yeah.
any guidance that you would want to give to our department, what sort of, projects we can give to students?
Okay, so first of all, of course, data science is something that is not only because it is the booming kind of area, all the people are talking about this. And I'm basically in this field. It's not because of that thing, but this method, these techniques, the statistical data science techniques will actually a kind of mathematical application that are directly related to the real life application, real life problems. So what I would recommend students, they should get some courage read about these techniques, and they should come out their comfort zone, whatever the mathematical courses they are doing, and they should expand their expertise, and they should involve they should get involved in this type of projects where we have some kind of statistical analysis. So what I would recommend, the project component, whatever they should do, major chunk should be based on a statistical technique, data science techniques.
Sir, any softwares or any kind of programming language that they have to they need to learn?
Of course, for the yes, for the statistical methods, we have a platform, open platform, that is for free. That is called R. Okay, so R is basically very useful, and I would recommend that if they are doing any kind of programming courses, then they should also learn this R.
Would that be easy for our students, sir?
If they are able to do this C++.
Yeah, they have the C and C++.
So this R, the R and SAS and Python, these are not the programming language. These are the softwares. Okay, these are the packages. If somebody is very good in these basic programming languages like C and C++, they must be very easily get these softwares.
Okay.
Yeah.
Sure, sir. Thank you so much, sir. Thank you so much for sharing your expertise with us.
Okay, so in future, if somebody from students also, if they feel like contacting me, just write to me, and I'm willing to help you even regarding the projects also. Okay.
Thank you, sir.
Yeah.
So I take the opportunity to express my gratitude on behalf of Head, Department of Mathematics, and the entire team. I would like to thank Dr. Satya Prakash Singh for taking your precious time out and consenting to grace us with your presence and guidance. Thank you, sir, for sharing with us that linear regression for data science combines different fields of mathematics, statistics, and computation in order to interpret data for the purpose of modeling. Indeed, you made us clearly understand various models of linear and nonlinear regression. Thank you for briefly throwing light on least square estimation model solving with an optimization techniques. So may I now request all the participants to enable their videos for the photograph.
Navya, are you clicking pictures now?
I request all the students, please enable your videos.
I think it's done.
Thank you, sir.
Thank you, sir.
Thank you. So
Navya, will you share feedback link, ma?
Check, Navya, if you can unmute yourself. Can you? Yeah.
Yes, ma'am.
Navya, have you shared the feedback link?
Yes, ma'am.
Navya?
Yes, ma'am, I'm sharing.
Okay, okay.
Yeah. Ma'am, I share.
Yeah. Girls, please fill the feedback form. Ma'am, shall we wind up in 2 minutes?
Yes, ma'am. We can wind up.
Ma'am, I received 42 responses, ma'am.
Okay, Navya, I think we can wind up. Or shall we
Yes,
wait for
ma'am.
some time? Shall we wait? Because see, now 20 more participants are around 19 participants are there.
Yes, ma'am.
Girls, please fill the feedback.
We'll
form.
wait for 5 minutes, ma'am.
Okay. Where are you, Navya? Are you in the hostel?
Ma'am, it's recording.
Ma'am, we can end the meeting, ma'am.
Yeah.
Girls, please fill the feedback form.
Japmala, Navya, Saujanya, Sabha ma'am. Bye. Take care.